2006 AP Calculus AB, free response question number 4. Rocket A has positive velocity v of t. Why does it have positive velocity? Because it's being launched, and as it is being launched, it's going up. It's not going down, so it has only positive velocity. So we have rocket A has positive velocity v of t after being launched upward from an initial height of 0 feet at time t is equal to 0 seconds. The velocity of the rocket is recorded for selected values of time over the interval from 0 to 80 seconds as shown in the table above. So this is an example of a problem in which a function is represented by a table of values, and we say this function is represented numerically for that reason, with ordered pairs. Now, we had just finished some assignments having to do with functions that are represented by graphs, graphically. The great thing about functions that are represented numerically is you can easily take these ordered pairs that are given and you can plot them, as I've done here, and you're able to visualize the information. So it becomes like a problem in which the function is represented graphically, tying back to what we just completed. So part A says find the average acceleration. So we'll get to that in a little bit, but let's read A and B. We're going to do parts A and B in this lesson. Part A says find the average acceleration of rocket A over the time interval from 0 to 80 seconds. Indicate units of measure. And part B says, using correct units, explain the meaning of the definite integral of the velocity function with respect to time from 10 to 70 seconds. In terms of the rocket's flight, so we want to explain what this means in terms of the rocket's flight. Use a midpoint Riemann sum. What is that? With 3 subintervals of equal length to approximate the value of this definite integral. So first of all, what does it represent, and what is its approximate value? So let's go ahead and do part A, and then we'll look at part B. And for doing part B, it's helpful for you to be able to visualize the given information by plotting the ordered pairs and looking at the information that's presented visually or graphically. So let's look at part A, which does not really require us to do the graph, but let's look at part A. Find the average acceleration. So the average acceleration of rocket A over the time interval from 0 to 80 seconds. Indicate units of measure. So what is acceleration? Acceleration is the rate of change of velocity with respect to time. So to find average acceleration for part A, you need to find the change in velocity and divide by the change in time. So that's what we need to do for part A. So if you want to find the average acceleration of the rocket on the time interval from 0 to 80 seconds, you need to find the change in velocity. So what was the velocity of the rocket at 80 seconds? And subtract from that the velocity of the rocket at 0 seconds. That would give you the change in velocity. And then you need to divide by the change in time. So the time is going from 0 to 80 seconds, so the change in time is 80 minus 0. So the average acceleration on the time interval from 0 to 80 seconds is given by the change in velocity divided by the change in time. So what is that? So we've got the velocity at 80 seconds is 49 feet per second, minus the velocity at 0 seconds is 5 feet per second. And you see where I'm getting that information. It's coming from my table. I know the velocity at different times. And divide that by the change in time, which is, of course, 80 seconds. So 49 minus 5 is 44. Divided by 80, you can reduce that to 11 over 20, or just leave it like this. That's fine too. What are the units for this average acceleration? Well, in the numerator, you have a change in velocity. And velocity is measured in feet per second. And then in the denominator, you have a change in time. And time is measured in seconds. So it's feet per second divided by seconds, or feet per second squared. Those are the units for acceleration in this problem. So now we're done with part A. So let's take a look at part B. And part B says, using correct units, explain what this means. Well, you have here the definite integral of a rate of change function. Remember, velocity is the rate of change of position with respect to time. So you have the definite integral of a rate of change. And when you have the definite integral of a rate of change, what information does it tell you? It tells you the net change in the position of the rocket from time is equal to 10 to time is equal to 70 seconds. So we can, for example, say that x of t represents the position of the rocket at time t. So this definite integral would be x of 70 minus x of 0. It is the net change in position of the rocket as we go from time is equal to not 0, but actually 10. As we go from time is equal to 10 to time is equal to 70, it's the net change in position. But because the rocket is only heading in one direction, it does not change direction, it's always going up on this time interval, this is also going to be interpreted as not just the net change in position of the rocket between the two times, but because it's only moving in one direction, it's also going to be interpreted as the total distance traveled by the rocket in that time interval from 10 to 70 seconds, and that distance is going to be measured in feet. So that's how you would do the first part of the problem. So you're going to write for your response to explain the meaning of this definite integral in terms of the rocket's flight. You're going to write, this definite integral represents the total distance traveled by the rocket, and include units in feet, from time is equal to 10 seconds, which is the lower limit of integration, to time is equal to 70 seconds. So you see that sentence? It gives you all of the information represented by this definite integral in a very precise and complete way. So now we're going to take a look at the second part of part B, the second sentence. Use a midpoint Riemann sum with 3 subintervals of equal length to approximate the value of this definite integral. Now, this is where it really helps for you to take the information that's presented numerically and plot these ordered pairs so you can visualize this information, and that will help you tremendously with part B, where you're being asked to use a midpoint Riemann sum with 3 subintervals of equal length to approximate the value of the definite integral. So let's take a look at how we can accomplish that. So first of all, we have our time axis and we have our velocity axis. The time is measured in seconds and the velocity is measured in feet per second. So if you take a look at these ordered pairs, we have 0, 5, so I find 0 for time and 5 feet per second for velocity, and I plot that here, and then I have 10, 14, and then I have 20, 22, and then I have 30, 29, and then I have 40, 35, and then I have 50, 40, and then I have 60, 44, 70, 47, and 80 seconds and 49 feet per second. So I take these ordered pairs and I plot them, and of course I don't really know what's happening in between these times, but it would be reasonable to assume that there is a smooth curve giving us the graph of the velocity function. So I have the points that are given. The graph of the velocity function is probably something like this, right? We're almost certain that it's going to be something like that. So how do you interpret the meaning of this definite integral? We've already talked about that. It represents the total distance traveled by the rocket in feet from time is equal to 10 seconds to time is equal to 70 seconds. But now, in the second part of part B, it's asking us to use a midpoint Riemann sum with 3 subintervals of equal length to approximate the value of this definite integral. So what we have here is the graph of the velocity function. And when you see the definite integral of the velocity function from 10 to 70 seconds, you're going to interpret that definite integral as the area under the graph of the velocity function above the time axis from time is equal to 10 to time is equal to 70 seconds. So the exact value of this definite integral is the area that's under the velocity curve. But we don't really have a rule for the velocity curve, so we can't really find the exact area. But what we can do is we can go ahead and approximate this area. And how can we approximate this area? One way is to do exactly what we're being asked to do in this problem, and that is to use a midpoint Riemann sum with 3 subintervals of equal length. So let's break that down one bit at a time. So let's start with the 3 subintervals of equal length. So we have the interval from 10 to 70 seconds. So if you look at the interval from 10 to 70 seconds, how long is that interval? 70 minus 10 is equal to 60 seconds, right? So that's the width of our interval, 60 seconds. And if we want to divide that into 3 subintervals of equal length, you're going to divide 60 seconds by 3. And that's going to give you 20 seconds. So each subinterval will have a length of 20 seconds. So these are my subintervals. From 10 to 30, that's my first subinterval. From 30 to 50, my second subinterval, and from 50 seconds to 70 seconds is my third subinterval. So those are my 3 subintervals. I'll highlight them in red so they're easier to see. And what is it that we want to do now that we have our 3 subintervals of equal length? We have our 3 subintervals of equal length, and we want to use them to approximate the value of this definite integral, but in the way specified in the problem. In the problem, it is specified that we want to use a midpoint Riemann sum. A Riemann sum. What is a Riemann sum? A Riemann sum is a sum of products. So we're going to have a sum of 3 products, 1 for each subinterval. And the purpose of each product is to approximate the area that's under the graph of the velocity function and above the time axis in each of our subintervals. So then how will we do that? So our Riemann sum will be calculated using a midpoint Riemann sum. So basically, midpoint Riemann sum means on each of your subintervals, and we have 3 of them, right? Our first subinterval is from 10 to 30 seconds, our second one is from 30 to 50 seconds, and our third one is from 50 to 70 seconds. So for each one of them, I want to use a midpoint Riemann sum. So what is the midpoint of the first subinterval? It's 20. What's the midpoint of the second subinterval? It's 40. And what's the midpoint of the third subinterval? It's 60. So basically, I have identified the midpoints of my 3 subintervals of equal length, and I am going to say, okay, look at my table here. When time is 20, the velocity is 22 feet per second. When time is 40 seconds, the velocity is 35 feet per second. And when time is 60 seconds, the velocity is 44 feet per second. So how do we use that? We're going to go ahead and say a Riemann sum is going to give me a sum of products. And each product will give me an approximation of the area under the graph of the velocity function and above the time axis within the subinterval. And basically, a Riemann sum will give you an approximation of that area by using what? The area of a rectangle. So that's what we're going to see right here. So again, this is the midpoint, and from the table we know that The velocity at time is equal to 20 is 22 feet per second. So the width of this time interval is 30 minus 10, or 20 seconds. And you're going to multiply that by the height of this rectangle. And when you do that, you'll get the area of this rectangle. And the height of this rectangle is, from our information that's provided in the table, 22 feet per second. And look at this. When you multiply 22 feet per second by 20 seconds, seconds and seconds will cancel, leaving you with feet. So that's what we have here. We take the velocity at time is equal to 20 seconds and multiply by the width of the subinterval. So that's 22 feet per second multiplied by 20 feet, and that will give us 440, and the units here will be feet. And you have to do that 2 more times to find the areas of these 2 rectangles, and then you're going to add the areas of all 3 rectangles, and that will give you an approximation for the value of this definite integral, and the units would be feet, and that would be an approximation for how far the rocket traveled on the time interval from 10 to 70 seconds measured in feet. So let's go ahead and finish that. So now we're going to look at the second. Again, here's the approximate curve for the graph of the velocity function going through the points given in our table, and we're approximating the area that's under the graph and above the time axis from t is equal to 10 to t is equal to 70 seconds. So we're going to find the areas of 2 more rectangles. This is our next one, and we're going to do that by finding a midpoint Riemann sum. So the midpoint of this second subinterval is going to be at t is equal to 40, and looking at our table, we have this point on the graph of the velocity function, and that would be 35 feet per second for the velocity. So you're going to multiply that by the width of the subinterval, which is 20 seconds. So when you multiply feet per second by seconds, seconds and seconds will cancel, and you get 35 times 20, which is, of course, 700 feet. And then you're going to do the process one last time for the third rectangle here. Again, the midpoint of that subinterval is at time is equal to 60 seconds. Looking at your table, you have that at time is equal to 60 seconds, the velocity of the rocket is 44 feet per second, and you're going to multiply the number of seconds for the width of the subinterval by the velocity. And when you do that, you're going to get 44 feet per second times 20 seconds, and that's going to give you 880 feet. And when you add these 3 values, you get 2,020 feet for the approximate distance traveled by the rocket, measured in feet from time is equal to 10 seconds to time is equal to 70 seconds.